Hello, everyone. I'm Param Kadadi, and I'm joined with Ethan Dewick, Wyatt Welch, Nick No, and Luis Salas, and we are Elite Ball Knowledge. The Baseball Avoidance Multirotor, also known as BAM, is a NASA challenge out of NASA Langley Research Center. The challenge asks researchers to program a model drone to dodge baseballs. The BAM project is mainly about autonomous collision avoidance, which is a hot topic in the aerospace industry today. The key problems in this are perception, prediction, and planning. Our mission was to create a system that is able to detect the baseball, find its trajectory, figure out if there is going to be a collision with the drone, and if so, avoid collision by moving out of the way and return to its original path. BAM is primarily MATLAB and Simulink based, but it also includes high fidelity capabilities using Unreal Engine, Microsoft AirSim, and Robot Operating System 2.
State-of-the-art autonomous drone systems will typically employ multi-sensor simultaneous localization and mapping in order to sense the environment. And this system will combine data from LiDAR, cameras, IMUs, odometry, and it'll be creating a pretty well-rounded understanding of the environment that we can pull from. Using such a large-scale multi-sensor system would be outside of the project scope for us, so we decided to focus on one sensor type, which ended up being LiDAR. With LiDAR, it'll send out quick laser pulses, which are reflected off of surfaces. They can return to us and give us a point cloud, which is a 3D map of the environment. And the expectation for this system is that it would sense the baseball about 90% of the time, and it would generate high precision inputs when correctly tracking the ball's position. A LiDAR-based perception module was built, which mirrored real-life components which were selected in a trade study. And after early successful testing in a controlled Simulink environment, it was later incorporated into our BAM high-fidelity sensors. We managed to retrieve live LiDAR point cloud during a test run, which proves that there is long-term viability in a LiDAR system. However, it became pretty clear that pursuing a full LiDAR system was also going to be outside of the project scope, and this inspired a switch to a more simple system. We switched to using pure state noise, which ended up being an elegant solution to perception and gave us an adjustable, repeatable, and 100% consistent way to test each configuration. The pure state is fed by the baseball's current position data, and we add noise which will mimic the output of a real sensor suite. And the effects of adding this noise can be shown in the following charts. Here's 0% noise, 10% noise, and 50% noise.
To start prediction, we introduced the built-in extended Kalman filter, which is specifically for non-linear linear systems. The reason for this filter is its ability to produce state estimations of trajectory positions at the current time step, then looking forward from it and communicating it to the controller, essentially outputting the best estimates of true trajectory positions. One of the main benefits of the EKF is it allows us to properly predict the baseball's trajectory. This essentially gives the avoidance planner enough time to determine whether or not a collision will occur, as well as many other benefits listed below.
After processing the position using the extended Kalman filter, the forward predictions are processed in the next block. Using Euler integration methods, the baseball trajectory is found and sent to collision assessment to verify the distance from the drone and communicate to the planning system to determine whether or not there is a need for movement. Only the non-zero positional data is accounted for due to the zeros affecting the filter readings. And here we have some of the variable comparisons from the true position. The top graph represents the predicted positional data versus the true data, while the bottom graph represents the predicted velocity in the z direction 1 second ahead compared to the actual. As you can see in the lower graph, the predicted velocity in z referenced by the yellow line is read around 17 seconds in and has a spike down, which may have had an effect of some of our results later on.
In order to avoid poisoning EKF estimations with bad data while the ball is sitting, which trains the drone to believe the ball will remain static, we measure the true ball position and identify the first frame of movement, which triggers the avoidance bus, bypassing the standard desired trajectory or to safe trajectory pipeline that normally enters the BAM controller. which is seen at the bottom of the image. After the aforementioned EKF, we use a polyfit to estimate the ball's velocity around the current time, accounting for gravity using a higher degree fit. We predict the future ball's position and velocity by using Euler equations, as well as estimating the drag acceleration that would come from the wind. Within the collision assessment, we first estimate the drone's future velocity using Bezier functions and compare the future relative distance between the drone and the ball to the safe radius of 3 meters. If they are expected to interfere, then a flag is triggered and the avoidance planner is activated. Next, the avoidance planner performs three actions. First, it calculates the optimal avoidance path for the drone, which is perpendicular to the ball along the drone's current heading, which is both time and energy efficient. Next, we create smooth alterations in the magnitude of the departure from the current heading using fifth degree quintic polynomials. Finally, we determine the state switch based on the current vulnerability of the drone. There are four states: nominal, blend out, hold offset, and blend back. Each of these can switch to one or the other given the current change in the flag mode to the drone, which allows for immediate adjustments if the given information calls for it. These three aspects of the planner are combined, which creates the trajectory command, which itself replaces the drone's current desired trajectory. Next, we show the results of our EKF, as well as a set of simulated tests we have run. The EKF had extremely effective results, despite our outdated photo shown. The use of feedback-generated covariance updates keeps the estimated noise low, and the movement-based EKF and bus activation prevents the data from being poisoned via the standstill ball. Overall, our EKF is extremely efficient at most noise values. Here we have our predicted results, and we can see that we have a very high success rate for all of our images. Out of 100 tests shown, we have a very high success rate with an equally high avoidance distance. And the high avoidance distance is a recurrent issue in our data. Another interpretation of our results here show the ball and drone trajectories. One of the potential causes for the large movement in the drone's behavior is the lack of calibration of the quintic polynomials, which allows the ball to overreact to the incoming ball, the drone to react to the incoming ball. And here we have a few videos. The first one shows in the bottom right, you can identify the ball coming up and attempting to hit the drone, which avoids out of the way at the last second and then sort of spirals. This is a reaction that is common amongst most of our video samples. Highly unfortunate.
As a highly active research interest, this project has plenty of future work. Certain assumptions need to be replaced with empirical data, which reintroduces the high fidelity sensors mentioned earlier. More sophisticated prediction methods through computer vision and machine learning are also in order. And the program could also be moved from a simulation to a real life drone. That's it. Thank you very much.